Transaction. In SystemVerilog, we generate stimulus in terms of packets. We call it as transaction. So whatever the test bench you are going to create in SystemVerilog, it can be considered as transaction level model. Everything is going to happen in terms of packets. We don't want to do anything in terms of binary. Binary is good for design, but when it comes to test bench, the performance is critical. So we don't want to generate values like binaries, ones and zeros. We want to generate the stimulus in terms of packets. And this is how different kinds of packets will be generated during simulation, like write packet and read packet. And eventually the scoreboard also collects everything in terms of packets. That's why we need components like monitor. So here, if you look at the driver converts the packets into binary, at the same time monitor converts the binary values back into packet. So the scoreboard is going to compare all the values in terms of packets. And this is how we define the packet in SystemVerilog. You don't need to worry about the syntax. There is a data type called class. So the syntax would be like class n class, and this is the name of the packet. As part of the packet, we define various variables, different kinds of variables, and here we want to generate random values. So all the variables have to be defined as rand, and for every random variable we have to define constraint, because we don't want to generate pure random values. We want to generate constrained random values. What is constraint? Basically we want to define a valid range. So here in this case, the data as 64 bits, then the possible values could be 2 to the power 64. We don't really need to generate the values in the range 0 to 2 to the power 64. Maybe within this range 0 to 2 to the power 64, there may be a valid range. That's what we try to define using constraint. Also, as part of the packet, we define different kinds of methods. So it's something like we want to define all the variables. At the same time, we also want to define what actually we want to do with those variables. Whether we want to display the variables, whether we want to copy the variables, or whether we want to compare the variables maybe as part of scoreboard later on, right? So there will be different kinds of functions or methods like display method, compare method, or copy method. So the class will have all the random variables and functions. That's how basically we define the packet. Now let me explain how this SOC has been created. This SOC has got various interfaces like GPIO, general purpose IO, AXI, AHB, PIO, parallel IOs, AHB, SPI. These are all various pins. And this is how we have connected all the IPs inside. So the SOC has got chip control, which converts the GPIO values into AXI protocol. So basically all the values will be driven inside as per AXI protocol. There is a bus called AXI bus. We use protocols like AXI and AHB primarily for on-chip communication. When it comes to external pins, we always define them as general purpose IOs or parallel IOs. But in this case, I am showing additional interfaces also like AXI and AHB, because eventually the chip will have some more IPs, and then at the top, if you look at, the chip will have only PIOs and GPIOs. That's how it's going to be. All right. So here there is an on-chip bus AXI, and this is how we connect all the IPs inside. So here there are 4 IPs mainly. One is microprocessor, the other one is DDR, the other one is DSP, and the other one is Bluetooth Low Energy IP, and all the IPs will be connected through AXI bus. Look at this. Also, the chip has got two more modules. One is chip control, the other one is chip interface. This chip control converts the GPIO protocol into AXI protocol, because within chip everything will be communicated in terms of AXI protocol. At the other end, same thing happens. It converts the external protocol into AXI. So here this chip interface supports multiple protocols. It's your option, like you want to have different kinds of protocols like USB, SPI, UART. In this case, you want to support three different protocols: USB, SPI, UART. What it truly means is any external component which will have one of these interfaces can be easily connected with this SoC. So if the external IP is going to have UART, then you can connect UART with this PIO, and this chip interface will convert UART into AXI. So whatever the protocol interface you are going to connect with this PIO, eventually the chip interface is going to convert that particular protocol into AXI. So this module primarily does protocol conversion. All right. So at the top, if you look at the SoC has got GPIO, AXI, AHB, PIO, AHB, SPI. All right. So this is how you can look at SoC as black box. This SoC has got 6 major interfaces. So the verification environment should have all these interfaces, then only you would be able to connect the test bench components with design. We want to drive stimulus, we want to collect the values from design. Then we need to define all these interfaces even for the test bench also. So this is the test bench. In SystemVerilog, this is how we create the complete environment. Look at this. So we create a top level module, that is a Verilog module. Within top level module, we instantiate the SystemVerilog test bench. So this is SystemVerilog test bench. Precisely speaking, this would be test case, SystemVerilog test case. The test case will have the test bench. We will look at the details later on. And this is the design, and this is how the connections will happen. The test bench will have all the interfaces, and the design will also have all the interfaces: GPIO, AXI, AHB, SPI, AHB, PIO. This is how we make the connection. All right. And this is how the test bench architecture would look like for this particular SoC. You apply the same concept. This is SoC. The SoC has got all the interfaces, and for every interface we need to create driver and monitor, and we have to create separate generator. The generator will be connected with driver. Look at this. So here GPIO generator, this is GPIO driver, this is GPIO monitor. This is AXI interface, AXI generator, AXI driver, AXI monitor. This is AHB interface, AHB generator, AHB driver, AHB monitor. Same thing for SPI, AHB and PIO. Everything is protocol based, pretty straightforward. For every interface we have to create driver and monitor. And for every interface we need to create generator in this case, because every interface is different. For GPIO you need GPIO packet, for AXI you need AXI packet, for AHB you need AHB packet. That's how we will be creating different kinds of generators. And you have two major test bench components. One is the reference model, the other one is scoreboard. This reference model produces the expected values. So here in this case, this is SoC. So you can't expect it to be a networking component. It does data transformation. So obviously you need to have a reference model. In this case, I would say the expectation is DUT should work as per reference model. So this is our golden reference. Whatever the values that's generated by reference model is going to be expected value. So we connect all the monitors, look at this, all the monitors with the reference model. Look at this. So every time when you generate any value like GPIO packet or AXI packet or AHB packet, all the packets will go to reference model also. And we need to connect all the monitors with scoreboard also. But in this case, the scoreboard is going to collect only the output values. Here, every interface has got monitor. The monitor might produce different kinds of values. When you drive stimulus, it will produce expected values through reference model. And when the SOC produces output, the same monitor will collect output and it will post the output values primarily to the scoreboard. So the scoreboard is going to collect primarily the output from the monitor, and the reference model is going to collect primarily the stimulus. This is how you can visualize. So here you can't look at the interface something like input interface or output interface. Every interface is bidirectional. You can drive the stimulus, and then based on the stimulus, the DUT will produce output through same interface. So every interface is going to be bidirectional. While driving stimulus, the monitor will produce input values, and that will be sent to reference model, and eventually the reference model will generate expected values. So look at this. The GPIO generator generates GPIO packet. This is stimulus. So the monitor will post this GPIO packet to the reference model. It goes to reference model, and whatever the SOC does based on GPIO packet, the reference model will also do. And in this case, the reference model will produce the expected GPIO packet, and that will be sent to the scoreboard. So this will be scored in the scoreboard as expected value based on the data transformation. All right. Now let's say like the DUT processes the data and then it produces some output through some other interface like SPIO. So in this case, this particular monitor is going to produce output data, but this output data goes to scoreboard. So when the monitor produces input, that time the reference model gets the value. When the monitor produces output, it goes to scoreboard. And once the scoreboard collects the output data, then it's going to compare the output data with the expected values. That's how the test bench is going to work. Here the important thing is this test bench architecture is very similar to the standard test bench architecture that we discussed. The concept is for every interface we have to create driver and monitor, and basically we need to connect the generator with driver. In this case, the DUT has got multiple interfaces, so we need to create multiple generators. And we connect all the monitors with both reference model and scoreboard, and the reference model outputs will be connected with scoreboard. All right. Now let's go back to transaction. We discussed about transaction. Transaction is nothing but packet. You think of this SOC. It has got multiple interfaces. So we need to create multiple packets. Based on the packet definition only, the generator is going to generate transactions or packets. So we need to define HB packet, AXI packet, GPIO packet, PIO packet, SPIO packet, and a register configuration packet. Before running simulation, we need to configure the DUT. So obviously we need to define a separate packet called reg packet. I will explain it a little later.